Good evening, all. Hello, everyone. Welcome to Unacademy. This is Bhanu Prakash, expert in GATE and ESC coaching. I did MTech from NIT Kurukshetra. I have 10 years of teaching experience and I train many students throughout our country for different competitive exams like GATE, ESC, Transco, Genco, and many more PSUs. I can teach electrical machines and power electronics. BPC 10 is my referral code. So use this code, you will get 10% discount on Plus subscription as well as a Iconic subscription. And what are the benefits of the Plus and Iconic subscription? Okay. Yes. Good evening, Pawan. Good evening. What are the benefits of the Plus and Iconic subscription? Just wait a minute. By taking Plus subscription, we have some benefits such as one is you can get live classes from the top educators of the country, and also you can get structural schedule for 3 months, 6 months, 12 months, and 24 months, and you will get unlimited practice questions per subject wise, topic wise. Similarly, you will get test series per subject wise and topic wise. So these are benefits of the Plus subscription. By taking Iconic subscription, you can get these four benefits. In addition to these, you will get some additional benefits. One is a personal coach, study planner, expert guidance, ESC mains, questions and answers. What is mean by personal coach? Okay, if we will provide a personal coach, he will guide everything until you get a job or until you get a rank in the competitive exams, okay, like GATE and ESC. And we will provide the proper study planners. So that means how do we study for the GATE point of view, how do we prepare for the ESC point of view. So like this, we will provide everything in case of the study planners, and also expert guidance, ESC mains, questions and answers. So for mains, we will provide the proper EA preparation. So that is the proper questions, possible questions in the exam, and also expected questions in the ESC mains, and for that questions we will provide the answers. Okay, that is the ESC mains questions and answer. So for ESC preparation, this Iconic subscription is a best suitable. Okay, so this is a very suitable for the ESC preparation. And what about, okay, this is the BPC 10 is my referral code. Okay, use this code, you will get 10% to discount on Plus subscription as well as a Iconic subscriptions. Okay, so what is the price for the Plus and Iconic subscription? Plus is available for 12 months, okay, 18 months and 24 months. For 12 months, fee is the 27,225 rupees. For 18 months, fee is the 34,650 rupees. For 24 months, fee is a 39,600 rupees. 39,600 rupees. Okay, use my code BPC10. You will get 10% discount on the Plus subscription as well as a Iconic subscription. And also I will provide the personal guidance or for any queries. And okay, next one more subscription, that is a Iconic subscription. It is available for the 12 months and 24 months. For 12 months, fee is of 45,225 rupees after the 10% of the discount. Similarly, for 24 months, P is the 66,600 rupees after the 10% of the discount. Okay. So this part, okay, about the subscription and also price and what are the benefits of the plus and iconic subscription. BPC 10 is my referral code. Okay, use this code, you will get 10% discount on plus subscription as well as iconic subscriptions. Okay. Just wait. Okay, Pavan, is that clear, everyone? Is my voice clear or not? Just tell me, mention in the comment box. Okay, వినిపిస్తుందా అందరికి? Yes or no? Okay. So listen. In previous class, we had discussed about that is a switching characteristics of. Okay, this is the switching characteristics of SCR. Okay, and also we had discussed about the gate characteristics of the SCR here. So gate characteristics are, that is nothing but the variation of the gate current with respect to the gate source voltage. So it is the gate characteristics of SCR similar to the PN junction PN junction diode characteristics. Why? Because gate terminal is connected to the positive polarity of the p-type material, and this is the cathode is connected to the negative polarity of the n-type materials here. So that gate characteristics of SCR is similar to the gate characteristics, that is the static VI characteristics of PN junction diode. Okay, this part we have discussed, and also we have done that is a load line. Okay, gate characteristics. Okay, slope of the gate characteristics is a positive slope, but slope of the load line is a negative slope. So what is about it represents? Slope of the load line indicates, okay, that is the source resistance, gate source resistance. So all these points we have discussed in the previous class. So today we will discuss about, okay, one is the first part we will discuss about the ratings of the SCR, ratings of SCR, and after that we will discuss about how do we protect the SCR from the abnormal conditions. Okay, that's we can call, that is a protection of the SCR. Okay, got it, man? So what are the ratings of the SCR and how do we protect the SCR from the abnormal condition? What is the meaning of abnormal conditions? So that is the over voltage, over current, the rate of rise of current is a more the as compared to the specified rated value. The rate of rise of the voltage is a more. How do we protect the gate terminals? That is a gate protection, that is the thermal protection. Okay, how do we maintain the temperature within the limits? That's we call as a thermal protection here. So this part we will discuss in this class. Okay, so now initially, so what about why ratings is required? Okay, we have a question. So ratings of the SCR. So why rating is required? The reliable operation of the SCR can be obtained only if it is operated so such that its ratings are not exceeded. So each SCR is manufactured to a particular voltage, current, power, temperature limits within which they can operate it reliably. So we have a question. So ratings అనేది అనుకోండి. So ratings కు ఎందుకు అవసరం? Okay, compulsory we have to follow the rating. Suppose any electrical machine or any power semiconductor device. So we have to operate the device within the rated, exactly at rated value or less than the rated value. So for example, the rated current అనుకోండి, rated current, so that is a 2 kilo amps. Okay, 2 kilo rated current of the SCR is a 2 kilo amps, and rated power and rated voltage. Okay, rated voltage. Okay, let us assume it is a the 10 kilo. Okay, this is the 10 kVA and 10 kilo volts here. So that means it can allows the current of, okay, 2 kilo amps, okay, under on-state condition. And rated voltage in the sense it can block the voltage of the 10 kilovolts during the off state. So next one, rated power also mentioned. Suppose if it is operated, if the any power semiconductor device or any electrical machine is operated more than the rated values, then what will happen? So now temperature rise of the device increases enormously, so which may damage the device. Okay, that's why we operate the device or machine within the rated values. Okay, but that's we call the reliable operation of the SCR can be obtained only if it is operated, if the ratings are not exceeded. Okay, its operated values are not exceeded the rated values here. So therefore what we conclude here, the rated current of any device, okay, less than, so that is the, sorry, just wait. So the rating of the any SCR or any electrical machine or any power semiconductor designed by the manufacturer. So this is are mentioned by the manufacturer on the nameplate details. So these are mentioned, okay, by manufacturer on nameplate details. Nameplate, okay, details. So it was given like voltage rating, current rating, power rating here. So always operated current, okay, for example operated current, the less than or equal to the rated currents. This is the per reliable operation, okay, per satisfactory operation, like satisfactory operation. So what are the conditions to be satisfied here? So operated current of the current passes the device, so must be less than or equal to the rated current. Okay, and similarly the operated voltage, okay, this operated voltage, so it is also must be less than the rate, less than or equal to the rated voltage. Okay, similar another one, operated power, okay, this is the power handling capacity. So operated power in the sense power handling capacity, the less than or equal to the power rating mentioned on the nameplate details, that is the rated power here. So like this here, per satisfactory operation of the any device, so operated current must be less than or equal to the rated current. Operated voltage must be less than or equal to the rated voltage. Operated power is also must be less than or equal to the rated power. Suppose if it is more than the rated one, suppose here is a rated current is a, this is the rated current, rated voltage, and rated power is equal to, okay, this is the 20 megawatts, okay, this is the megawatts like. Suppose if it is a this instead of the rated current is a 2 kilo amps. Suppose if it is operated for 3 kilo ohms, so then what will happen here? The temperature rise at the junctions of the semiconductor device. The increases enormously, which may damage the device. Okay. Similarly, suppose if it is operated, the instead of the 10 kilovolts, it is operated for the year for the 15 kilovolts during the off state. Then what will happen here? So this is the temperature rise of the device increases enormously, which may damage the SCR. Okay, so that we cannot that is the per satisfactory operation, operated current must be less than or equal to the rated current. Operated voltage must be less than or equal to rated voltage. Operated power must be less than the rated powers. Okay, I repeat once again, the rating of any device is mentioned by the manufacturer on the nameplate details. So during manufacturing, designing of the machine, so your rating is based on the rating of any machine or any device is a mention based on the temperature rise. So how much temperature can withstand? Okay, like this we can design the machine. Okay. All of it clear now? Is that clear, everyone? Purpose of the rating. Why rating means? For satisfactory operation of the any device or SCR. So the rating should be less than or the rated values. The rated values means the value which is mentioned by the manufacturer on the nameplate details during the manufacturing. Okay. Yes. Thank you. Now, what are the various types of the rating of the SCR? So, one is a voltage rating, okay, voltage rating, current rating, temperature rating, and also power rating here. So, let us discuss initially about the voltage rating. After that, current rating, temperature rise, and the power rating. One by one, we will discuss. Now, what are the various types of the rating, voltage ratings here? So, first one, it is a peak working forward blocking voltage. Okay, it is represented with a VDWM. Okay, I will tell you very clear what is the mean by peak working forward blocking voltage. And second one is a peak repetitive forward blocking voltage. Okay, this is a peak repetitive forward blocking voltage. And third one is peak non-repetitive or surge forward voltage. It is denoted by VDSM. Okay, VDSM here. And fourth one is a peak working reverse voltage. So it is denoted by VRWM. Okay, VRWM. Next one, peak repetitive reverse voltage. Okay, it is represented with the VRRM. So peak repetitive or the VRRM is peak repetitive the reverse voltages here. And next one, peak non-repetitive or surge. Okay, this is a reverse voltage VRSM. Okay, that is the reverse surge the voltage, maximum reverse surge voltages here. And on state voltage drop, okay, it is represented with a VT. And gate trigger voltage, the VGT, and forward dV by dt. Okay, this is the rate of rise of the voltage rating. So these ratings are mentioned by the manufacturer. So during the manufacturing of the SCR here. Now let us discuss one by one. What is the mean by peak forward blocking voltage or peak repetitive forward blocking voltage and peak non-repetitive the surge forward blocking voltage. So we know that, okay, in SCR, so what are the modes of the SCR here? Already we have discussed this point. So what are the modes of the SCR? We have three modes of the SCR. One is one is reverse blocking mode. Okay, reverse blocking mode. and second one is the forward blocking mode, okay, and third one is the forward conduction modes. Okay, these are the three modes of operation. So in reverse blocking mode, SCR act as a open switch. Okay, here just like a, so ideally it act as a open switch, but practically what will happen here, some small amount of current the passes from the cathode to the anode terminals. Okay, so that is a anode is a made negative with respect to the cathode. Very small amount of the current passes from the anode terminal to the cathode terminal during the reverse blocking mode. But ideally we can say that this leakage, reverse leakage current is a very small, so neglected here. So that's why we can treat it as a this SCR is act as a open switch during the reverse blocking mode. Okay. Similarly, so there is a one more mode, that is a forward blocking mode. So what is the meaning of forward blocking mode here? SCR is anode of the SCR is a made positive with respect to the cathode terminals. Okay, anode of SCR is a made positive with respect to the cathode terminal. So very this junction J1 and J2, J1 and J3 are the forward bias and J2 is a reverse bias, due to which what will happen? So very small amount of the current passes from the anode to the cathode current, the cathode terminal. That current we treated as a forward leakage current. So if it is neglected, so therefore what will happen? In this mode also, the SCR is act as a open switch. Okay, open switch here. So now here is gate circuit is a open. Okay, forward blocking mode means the anode is a made positive with respect to the cathode, but IC is equal to 0. So that's why it is act as a open switch. Here also act as a open switch. So in forward conduction mode, so if it is the anode is a made positive with respect to the cathode and gate circuit is the given, then junction J2 will be breaks down, so that current flows from the anode terminal to the cathode terminal continuously here. So that's why in this mode the switch is act as a closed, okay, closed switch here. So now this is a closed switch. Okay, this is a open switch. Okay, it is a treated as the open switch. These are the modes of the SCR. Okay, modes of the SCR here. So now we have some terminology. What is the terminology here? So what is mean by forward blocking voltage, repetitive, non-repetitive, surge forward, similarly reverse, okay, working voltage, okay, peak repetitive voltage, and this is the non-repetitive voltages here. Suppose this is we have a one sine wave. Okay, this is the one sinusoidal supply. Okay, supply here. Got it? Just see here. This is the positive supply and the negative supply here. So this is let us assume supply voltage Vs here. So what about this ender for the positive supply? This is the forward biased condition. Okay, here SCR in the forward bias condition. Suppose I am giving supply. This is the my SCR. Okay. So మనం SCR కు పాజిటివ్ సప్లై ఇచ్చినాం అనుకోండి. సో ఈ కండిషన్ లో SCR is the anode is made positive with respect to the cathode, but gate is open. So now that's why this is called as a forward blocking mode. Okay, it blocks the forward voltage. Now suppose anode is a negative with respect to the cathode, the SCR can block the negative voltages also. Okay, so this is called exactly this voltage. Okay, here this is called as a, so now it is a peak voltage or the maximum, okay, forward voltage. Okay, forward voltages here. Now what about this one? So this is, we can say that, so it is a maximum, the here the reverse voltage, the reverse voltages here. Suppose here maximum forward voltage, or it is also called the peak forward voltage. Allah figure it point, the peak forward voltage, and it is also called the peak, the here this is the peak reverse voltages here. So it is working, okay, exactly under normal operating condition. So we need a sine wave. So it is a working condition. So this is called the working condition, normal working operating condition, or normal operating condition, normal working condition here. So that's why it is called as the maximum working forward voltage. Okay, now similarly, our peak working forward blocking voltage. Why? Because for this year, anode is made positive with respect to the cathode. So, but Ic is equal to 0. Okay, Ic is equal to 0. And another circuit, anode is a negative with respect to the cathode. Okay, with respect to here, anode is a negative. So, with respect, this one is a negative with respect to the cathode terminal. So, there is this is the reverse circuit. So, for positive half cycle, the SCR in the which mode here? The SCR in the forward blocking mode, and the per reverse, this the negative half cycle, SCR in the reverse blocking mode. So that's why what we conclude. So this is under normal operating conditions, under normal operating condition, or under normal working conditions. Okay. So this voltage is treated as a maximum working forward voltage. Now similarly, what about this voltage? The reverse working voltages here, or maximum the reverse blocking forward voltages here. So maximum the peak forward working voltage, the peak reverse the working voltages. Like this you can classify. So just example I have mentioned that. So what is the meaning of peak working forward blocking voltage and peak repetitive forward blocking voltage, or peak non-repetitive forward surge voltages here? So desirable waveform is a sinusoidal, but actually we cannot get the sinusoidal wave due to the load parameters and also commutation process. So we will get this type of the waveform. So now here is a positive half cycle. Okay, it is a positive half cycle, and this one is the negative half cycle, and similarly positive half cycle, and this one is the negative half cycle and positive half cycle again, like so on. So now in this period, okay, from year to year, okay, exactly this period, we can treat it as a time period T here. Okay, time period T. All of it clear now? What is the meaning of the forward voltage and reverse voltage? Suppose here if just imagine there is no spikes. Okay, this is a exactly at the sinusoidal voltage. Okay, exactly at sinusoidal voltage. So now this is treated as the forward. Okay, this is the forward working peak forward working voltages here. Okay, like this. This is the first term. So maximum positive voltage. Okay, maximum positive voltage under normal operating conditions is known as the peak working forward blocking voltages here. So this is the maximum forward voltage which can block the voltage, which can block the SCR. So now that is known as a maximum forward the working blocking voltages here. Okay, all of it clear now? So this is what about this part? Okay, this is a waveform. So mid sinusoidal waveform this kondi first. Okay, let us take sinusoidal waveform. Okay, like this. So here there is no spikes in the positive half cycle. There is no spike voltage or surges in the negative half cycle. Similarly, there is no spike or surges in the positive half cycle, the next half cycle here. So now this voltage is known as the forward. Okay, this is the peak forward blocking voltages here. Okay, so that is nothing but the peak working forward blocking voltages. So what is the nomenclature to represent this one? What is the meaning of forward blocking voltage, forward conduction voltage, non-repetitive voltage? Like, okay, we can represent. Just wait. Okay. So this is the maximum, the positive voltage, and this one is the maximum negative voltages here. So that in this maximum positive voltage, SCR in the forward blocking condition, and in this voltage, SCR in the reverse blocking voltage condition. So that's why what we represent here, VDWM, so VRRM or VDRM, the VDSM, okay, like, so where F in the means, okay, F in the sense, so where F we can say that F is a forward voltage, okay, forward, okay, like. And next one, so what about the R here? The R in the sense it is the reverse, okay, reverse. And T is a on state, okay, T is the on state, and D is a forward blocking state with gate circuit is open. So this is the forward blocking state with gate circuit is open. Gate circuit is open. Got it? Okay. And next one more parameters also there here. What about the S? Okay, here is a T in the sense here, small t, that is a trigger voltage, okay. And S is the surge or non-repetitive, okay, the surge or non-repetitive voltage. And next one, R is the small r, so that is a repetitive voltage, repetitive, okay. And W in the sense working, okay. These are the some terms belongs to the, so this the ratings of the SCR. So VDWM is nothing but, so here D is called forward blocking voltage with gate circuit is open, and W is the working, and M is the maximum value here. So that's why it is called peak forward the blocking voltage, okay. This is the peak forward, the peak working forward blocking voltages here. So that means maximum voltage of the SCR, so which can block during the forward biased conditions, okay, or forward blocking mode. So that voltage is known as the peak forward the blocking voltage. It is represented with the VDWM. And next one, peak repetitive forward blocking voltage. So what is the meaning of peak repetitive forward voltage? Suppose in this waveform, okay, here is so there is a surge here, okay, in the positive half cycle, and similarly here also there is a surge in the negative half cycle, and there is a spike in the positive half cycle here. So this voltage is known as, okay, peak repetitive forward voltage, okay, forward blocking voltages here. So this is called the peak repetitive forward blocking voltage, okay, forward blocking voltage, okay. It is a repeated per every cycle. Suppose from year to year, in this time period, in the positive cycle there is a spike, and the next cycle also there is a spike, and the third cycle also there is a spike. So that is the maximum forward voltage that can repeated per every cycle, okay, every positive half cycle. So that voltage is known as a peak repetitive forward blocking voltages here. And next one, the peak repetitive, that is a peak the non-repetitive surge forward blocking voltage. So peak non-repetitive surge voltage here. So this voltage, okay, from year to year, so this is comes in a cycle, okay. Here is a comes in the only once, okay, only once in the complete cycle. So now this is called the peak voltage, the peak non-repetitive, so non-repetitive forward blocking voltage, okay. Similarly, so what about the reverse side? Okay, this voltage is known as a the forward, that is a peak working the forward blocking voltages here. Okay, this is the peak working forward blocking the reverse blocking voltage. Now this is the repeated every half cycle. Okay, it is a positive negative half cycle, first negative half cycle, and also next negative half cycle, and like so on. So it is a repeated per every cycle. So that's why it is treated as a the reverse, okay, repetitive, okay, the reverse, okay, this is a repetitive reverse blocking voltage. That is the maximum value. So that is the maximum the reverse repetitive blocking voltage, and this voltage comes at a time once. Okay, that is the entire cycle only once. That's why it is called as a surge voltage or non-repetitive to the reverse blocking voltages here. Okay, like this you can define. So what is the meaning of the surge voltage, repetitive voltage, and also blocking voltages here? Okay, there are the 6 voltages. So here in the first one, so we know that this is the reverse, okay, forward breakover voltage. Okay, so now this voltage VDSM, okay, this is the surge voltage is a less than the forward breakover voltage. And next one, the reverse, okay, forward, this the forward blocking voltage, the repetitive forward blocking voltage less than this value. And next one, it is a working voltage, normal working voltage is the less than the. So what about this ratio? So VDWM less than the VDRM, the less than VDSM, and it is less than the VBRM. So reverse breakover voltage. And here similar also, okay, this is the reverse working voltage, and the reverse, okay, this is the reverse repetitive voltage, and this is the reverse non-repetitive voltage, and this is the reverse break the down voltages here. So reverse breakdown voltage is more as compared to so VRSM, and it is also more as compared to VRRM, and it is also more as compared to VRWM. So what is the relation here? So this is the VBRR. So this is a VR. Okay, just wait here. So VBRR less than the VRSM, and it is less than the VRRM, and it is a less than the VRWM. So all of it clear. So that is the reverse breakover voltage. Okay, this is the reverse breakover voltage VBRR is a greater than the VRSM. Okay, it is also greater than this is the VR, maximum negative voltage, and this is also greater than the VRRM, and it is a greater than the VRWM. So working voltage is less as compared to the this VRM. So these are negative voltages, and this one is the positive voltage. Okay. All of it clear now? So what is the meaning of the reverse repetitive voltage, forward repetitive voltage? And next one, on state voltage drop. Okay, it is a very small. So that is a 0 to 0.5 volts to the 1 volts. The how much amount of the voltage during the on state. So whenever SCR is on, so it is a very small value. And gate trigger voltage is here. So gate trigger voltage means the gate source voltage to turn on the SCR. How much amount of minimum voltage to turn on the SCR to the gate to cathode terminal voltages here. And forward dV by dt recurrent. It is also mentioned on the nameplate details. So that is the rate of rise of the voltage, okay, during the turn on the SCR. Okay, so these are complete the voltage ratings of the SCR: peak working forward blocking voltage, peak repetitive forward blocking voltage, peak non-repetitive surge voltage, the peak working reverse voltage, peak repetitive reverse voltage, peak non-repetitive surge reverse voltage, and on state voltage, gate trigger voltage, and forward dV by dt the ratings. Okay, is that clear everyone? M means the M is a maximum power. M in the sense maximum. So that is the without any spikes, that is the normal working voltage. So these spikes are repeated continuously in the every half cycle, that is the repetitive to the voltage, that is the maximum repetitive forward blocking voltage. So now here in the negative side, maximum repetitive to the reverse blocking voltage. Okay, now this is only once in the complete cycles. Okay, here, so that's why it is a non-repetitive or surge voltages here. So maximum non-repetitive reverse blocking voltage, and this VDSM is what? So maximum non-repetitive forward blocking voltage. That means how much amount of the voltage. Okay, here under normal operating condition, positive voltage under normal operating condition, that is the forward working, okay, blocking voltages here. Okay, any more doubts? So what is the relations here? So these are the relation. Forward breakover voltage is greater than that is a normal working voltage. It is also greater than the repetitive working voltage, or the DSM, and is also greater than the non-repetitive and also working greater than the voltages level. Now in the reverse manner also, the reverse breakover voltage is more as compared to the surge voltage, and it is also greater than the reverse repetitive voltage, and is also greater than the working voltages here. So these are working voltage and repetitive voltage and non-repetitive voltage. Any more doubt? Okay, now let us discuss about the current rating of the SCR. What are the current ratings of the SCR? One is the average on-state current. Okay, it is represented with the IT average. Okay, actually IT is the thyristor current average. Next, RMS on-state current. Okay, that is the IT RMS current. Okay, thyristor, the RMS value of the current. So next one, surge current. Okay, this is the surge current means non-repetitive maximum voltages. ITSM as like a voltage. Now this is the I square R rating. Okay, this is the I square R. Okay, I square that RT rating here. Okay, this is the I square the ratings. I square T rating here. So now this is the how much temperature rise. So next one, di by dt here, the rate of rise of the current. So we know about latching current, holding current and gate current. So what is the meaning of latching current? Latching current is related to turn on of the SCR, whereas holding current is related to turn off of the SCR. So minimum current required to turn on the SCR, minimum anode current is required, or minimum anode current above which the SCR maintain the turn on state continuously. And holding current means here minimum anode current below which SCR, the SCR is the under turn off conditions. That is the bringing the SCR from the forward blocking mode to forward conduction mode. So that is the meaning of holding current. Now what about average current here? So now it is specified with the average current. Suppose if it is a DC supply. So now it is the average value is a this is the average values here. Suppose it is a specified with the AC supply. Okay, then what will happen? So now it is a specified with the AC supply voltages here. So here per average value of the AC supply is equal to 0. So that's why RMS on state current, IT RMS, and surge current means maximum non-repetitive current. That is a surge current. So now this one is to select the protecting device, I square R rating or integral rating also. It is also called the integral rating. So now it is required to select. Okay, this is the to select the proper the protective elements such as the fuse or the circuit breaker. That select the circuit breaker say. Now rate of rise of the current. How much time? Here di by dt. The rate of the rise of the current. It is also specified on the nameplate details of the SCR. And latching current also specified on the nameplate details of the SCR by the manufacturer. So what is the meaning of latching current? the minimum current, the minimum value of anode current. So latching current in the sense minimum value of anode current above which SCR maintain turn on state continuously is known as a latching current. So next one, holding current in the sense it is the minimum value of anode current below which SCR comes from forward conduction mode to forward blocking mode. Okay, so now SCR is operated in the forward conduction mode for the turning off, that is nothing but the above which turn off of the device. So that latching current is related to turn on process of the device, holding current is related to turn off process of the device. So what about the gate current? Okay, gate current it is also mentioned on the nameplate details. So what is the meaning of gate current? How do we define the gate current here? So minimum gate pulse is required, or minimum the gate current required to turn on SCR satisfactory. Okay, that current is the satisfactory is known as a gate current. Okay, all of it clear now? Okay, this is the SCR average on-state current is the maximum repetitive voltage. Okay, this is the maximum repetitive current during on-state here. And what about this surge current here? So it is a maximum non-repetitive. So now the non-repetitive current during on state. So repetitive forward anode current during the on state. So that is the surge current. So now it is for the AC supply. We have to calculate the maximum RMS current. That is the maximum repetitive RMS value of the on state current. Okay. So that is the current rating. All the voltage rating and current ratings are mentioned by the manufacturer and the nameplate details during the manufacturing of the SCR. Okay, any more doubt? So this is the discussion about the ratings. Okay, ratings is required so to operate the device for the satisfactory. If we don't know the ratings, then what will happen? We cannot operate the device's reliable operation. So here for satisfactory operation, what we have to do here? Operated current must be less than the rated current, less than or equal to the rated current. Operated voltage also must be less than the rated voltage, and operated power is also must be less than or equal to the rated powers. Okay, all the rating of any device, are not only this power semiconductor device, all electrical machines are mentioned by the manufacturer. So on the nameplate details. Okay, the rating of any device is the mention, or device is a mention based on the temperature rise, how much temperature comes from the device. So in order to limit this temperature value, so this is operated within the rated value. So suppose if it is operated more than the rated value, the temperature rise of the device increases enormously, so which may damage the device permanently. so that we don't want to operate the any device more than the rated values. Okay. That is a during the turn on pass turn up latching current is the minimum current only. Minimum value of the anode current required that to turn on the SCR or to maintain the on state continuously. That is the anode current. Suppose if we see the characteristics, okay, these are the characteristics point of view. So here is a forward current or anode current. Okay, it is the VAK and positive value. So now this is the minus VAK. Okay, it is the negative voltage and this one is the positive voltage. Pavan. So what will happen here? So without any gate pulse, okay, here this is the forward breakover voltage. So now here is a forward blocking mode. Suppose whenever gate pulse is given, this current suddenly increases to, okay, here, okay, from this point. So now at this point, okay, here minimum value of the anode current, okay, minimum value of anode current above which SCR maintain the turn on state even if gate signal is removed. Okay, suppose E position దగ్గర నేను gate signal ఇచ్చేసి నేను remove చేసినా కూడా SCR maintain the forward conduction mode. So that is nothing but here minimum value of anode current above which, okay, above which, so this SCR maintain forward conduction state continuously with the gate signal is removed. Okay, that current is known as the latching current. Okay. Yes, Pavan, have we got it now? So this is the ratings of forward blocking mode and forward conduction mode. So power rating is a power dissipation. There are the two power ratings here. So one is a average power rating. Okay, next one the average power losses are also gate power loss. Okay, gate power loss. And second one is, so this is the on state power loss. On state power losses. These are the power rating. Power dissipation in the SCR produces the temperature rise in the junction regions. So dissipation power in the SCR includes forward power dissipation. So during the turn on process as well as a turn off process and also gate process here. So now completely already mentioned this part in the basics. So now it is a complete power losses is equal to power loss. So that is a blocking power losses. Okay, blocking and also conduction power loss plus conduction power loss and also that is the switching power loss. Okay, this is the complete power losses here. So blocking power loss means average power loss during off state. So conduction power loss means during the on state. Switching power loss means so to turn on the device from the on state to the off state and off state to the on state, vice versa here. And also in addition to this, then so this is the device the power losses. Okay, device or power loss. One more is the gate power losses during the gate also. So in order to the turn on the device, we have to provide the gate signal to the device. So due to which some amount of the power is wasted, okay, in the form of the heat. So these power losses is known as a gate power losses. So average power losses also mentioned on the nameplate details by the manufacturer. Similarly, gate power loss also mentioned by the manufacturer during the manufacturing of the device. Okay. So now let us discuss about the protection of the SCR. So this is a very important for exam point of view. Okay. So for reliable operation of the SCR, what will happen? See. Okay, for reliable and efficient operation of SCR, it is designed to operate within the specific voltage, current and power rating. So it must be protected from the abnormal operating condition. And what are the abnormal operating condition? So that is a maybe over current, over voltage, high di by dt and high dv by dt, and thermal, the high temperature rise, and also high value of the gate current and gate voltage, and some noise comes from due to the communication line. So these are all abnormal conditions here. So that's why here various protection schemes are available for satisfactory operation of the SCR. And what are the various protection schemes of the SCR? So one is a over the, okay, this one is the first one. So over current protection. Okay, this is the over current protection. Okay, and second one is over voltage protection. Okay, third one is a the dv by, okay, that is the di by dt protection. Di by dt protection. So that means the rate of rise of the current protection. And fourth one is the dv by dt protection. So these are the different protection schemes. And fifth one is a gate protection. How do we protect the gate terminal, or that is the gate terminal of the SCR? That is a gate protection. And next one is a thermal protection. So how do we protect the SCR for high temperatures? Okay, that we can call it as the thermal protection of the SCR. So over current protection, over voltage protection, di by dt protection, dv by dt protection, the gate protection, and also thermal protection here. Now let us discuss one by one what is what is over current and what is a over voltage. How do we protect the device from the over current? How do we protect the SCR from the over voltage? And what is a di by dt? So how do we protect the device from the high di by dt? How do we protect the device from the high dv by dt? And how do we protect the SCR from the gate protection? Similarly, how do we protect the SCR from the thermal protections here? Or how do we protect the SCR from the high temperature rise during the off state and on state? So this part we will discuss one by one. Okay. So now first one, the protection, over current protection here. So first we have a question. What is the mean by over current protection? So over current protection means supply current, okay, is greater than the rated current. So which is specified by the manufacturer on the nameplate details here. So let us assume this is a, so supply current is a greater than the specified the rated current on the nameplate details. That is nothing but here over current. Okay. So now here this, for example, the example point we have taken the rated current. I rated the rated current of SCR. Okay, SCR here. So that is equal to 3 kilo amps is there. Okay, 3 kilo amps. Suppose if it is supply current is a, if the supply current I supply the is a, this is a greater, that is equal to the 4 kilo amps, then what will happen here? So it is operated over current position here. So if supply current is greater than the rated current which is specified on the nameplate details, so that is then the machine, then the device is said to be under over current conditions. So how do we protect the SCR from the over current protection here? So now if it is there, suppose this can be protected from the combination of the circuit breaker and the fuse here. So this rating of the circuit breaker and the fuse can be obtained by using I square R rating. Already I mentioned I square rating or integral current rating here. So this is the circuit breaker and the fuse. So these two are connected in series with the SCR as shown in the figure. Suppose if in this case, if supply current is a greater than the rated current, so then what will happen? Junction temperature exceeds the rated value and the device may gets damaged, okay, which is undesirable. So that's why what we have to do here. So in order to protect the SCR from the overcurrent, so we have to connect a circuit breaker and fuse in series with the SCR as shown in the figure. So this is a combination of the circuit breaker and the fuse. Okay. All of it clear? So that is the meaning of overcurrent. Overcurrent in the means supply current is a greater than the rated current. So which was specified by the manufacturer on the nameplate details during the manufacturing of the SCR. Okay. Next one, over voltage protection. What is the meaning of over voltage protection? Supply voltage is a greater than the rated voltage which was specified by the manufacturer on the nameplate details. Suppose here is a supply voltage is greater than the, okay, this is the greater than the rated voltage. So rated voltage is mentioned on the nameplate details. Suppose if it is operated more than the rated voltage, that is known as a over voltage condition. How do we protect the device from the over voltage condition, or what will happen due to this over voltage condition? So we know that in suppose anode is a made positive with respect to the cathode. Okay, this is a anode. One is a first P1 layer, P2 layer, and so this is the P1 and the P2, the N1, the P2 and N2 layers here. So this is the cathode terminal and this one is the anode terminal, and gate current IC is a open circuit. IC is equal to 0. So now here anode voltage, okay, this is a, so under anode is a made positive with respect to the cathode, then what will happen? So junction J1 is a forward bias and the J3 also in the forward bias and J2 is the reverse bias here. So now if it is anode to cathode voltage more than the, okay, this rated value, okay, rated value, then what will happen? So they may chance to get the, this is the junction this is the junction will be, so here the junction will be the breakdown, current flows from the high amount of current flows from the anode to the cathode condition here. So now this type of results is nothing but false turn on. False turn on means we don't want turn on some particular voltages. So now here it can be turn on, so with a voltage which is not required at this time. So that is nothing but here false turn on of the device. So due to which what will happen? Damage the SCR, and it can be protected from the over voltage by using the metal oxide non-linear resistor. So it is also called the varistor here. So how do we connect this varistor? Varistor is a connected, so across the SCR terminal, okay, as shown in the figure. So now this is the non-linear resistor here. What is the meaning of non-linear resistor? So that is the IV characteristics, that is the voltage I characteristics, the voltage and I value here. So now these IV characteristics are non-linear. Okay, this is the IV characteristics are the non-linear here. So like suppose per minimum value, per low value, this is the low voltage. Okay, this is a resistance value per low voltages here. And this is the resistance value per I voltage. Okay, like this. So now I voltages condition. So now it is a value is a high. Okay, this is the low resistance and this one is the high resistance value. So now it is this is simply non-linear. This is a non-linear resistor. That's we called as a varistor here. So now here what are the characteristics here? So per low voltage these characteristics are linear. Per high voltage here these characteristics are high. So now whenever this is a high voltage, okay, this is a, so it can reduce as the voltage because of this non-linear characteristics. So now it is a, per low voltage it is the same small amount of voltage across the device. Per high voltage then what will happen?
So this varistor can reduce this over voltage because of this non-linear characteristic. That's why varistor is connected across the anode to the cathode terminal of the SCR as shown in the figure to protect the SCR from the over voltage. Okay. Okay, is it clear? What is the meaning of over voltage and what is the condition here? Over voltage in the sense supply voltage greater than the rated voltage. How do we protect this SCR from the over voltage? So it can be protected by connecting the varistor, okay, across the device, across the SCR as shown in the figure. So varistor is a non-linear resistor, the metal oxide non-linear resistor. So for low voltage, it offers the low amount of the voltage. For high voltage, what will happen due to non-linear characteristics? It offers the very low voltage across the SCR. Okay, it can limit the increment of the voltage. Okay. So this is the meaning of over voltage protection. So next one, di by dt protection. Di by dt is the rate of change of the current in a device. So it is protected from the high di by dt by connecting an inductor in series with the SCR as shown in the figure. So what is the meaning of di by dt protection? So for example point I have taken, the rated current is equal to I rated is equal to the 100. Okay, this is equal to 100 amps I have taken. Example point I have taken, the rated current of the SCR is equal to 100 amps. Okay, so now di by dt, okay, rate of the rise of the current. Okay, this di by dt. So it is the rate of rise of the current is equal to, so that is we have taken the 30 amps, okay, per microseconds. Okay, this is the di by dt. So amps per microseconds here. Okay, this is the di by dt rating. So it is a given the di by dt and I rated one. So what will happen? See, so actually it can allows the 100 amps of the current during the turn on process. Okay. But rate of rise of the current is a 30 amps per microsecond. So which is a less than the specified one. Okay, specified the rated current. Are you getting my point? The rated here di by dt is a less than the specified rated current on the nameplate details of the SCR. But why it is? The local hot spots occur in the device which may chance to get the damages here. What is the reason? See, suppose I divided the SCR into 4 parts. Okay, like suppose this is the one SCR, and similarly this is the P1 and N1 layer, and this is also another SCR like. So now here we have taken it is a T1 and T2, and this is the T3, and here T4 here. Okay, T. So now like this, okay, we have a total current is equal to, that is a 100 amps of the current. Okay, 100 amps of the current, but it is because of this, whenever positive gate pulse is given, okay, at this case, so here how much amount of current it can withstand. Okay, this T1 can withstand. So for example point, I have divided into the 4 SCRs. Okay, this is that one SCR cut into the 4 pieces just at the time of the starting. So now it is a T1, T2, T3, T4. So T1 is the SCR which is very nearer to the gate terminals. The T2R is a SCR which is the nearer to the gate terminal after the T1. And T3 is T3 is the SCR which is the nearer to the away from the gate terminal after the T2. So T4 is a very away from the gate terminal, okay, during the turn on process. So when anode is made positive with respect to the cathode terminal, so then what will happen? 100 amps of the current. So now here some IZ current is given. So then what will? IZ is not equal to 0. So high amount of current is passes through here. So now this current is a 25 amps. Now T1 can allows the current of the 25 amps, and similarly T2 also allows the current of. So now this is the current of the 25 amps, and similarly T4 also, T3 also allows the current of the 25 amps. Now this also allows the current of the 25 amps. So now total current passes from the anode to the cathode terminal. So that is equal to, okay, here how much amount of the current? 100 amps of the current. So once, okay, once gate is triggered, then what will happen? The current passes through the T1 is the 25, okay, 25 amps. But rate of the rise of the current is a 30 amps, okay, 30 amps here. So now rate of rise of the anode current. So now here is a rate of the rise of the anode current is a 30 amps at the time of the gate signal. But here, so once it is a triggered, so it is a more than the rated values. Okay, rated value of this T1 is a 25, but which is a more than this rated value. So they may chance to get the local arc spots. Okay, local arc spots here. So like this local arc spots, temperature rise up the junction which is nearer that is a temperature rise of the the temperature rise up the layer which is nearer to the gate terminal increases here. So now again, so once it is a turn on, okay, turn on here. So now it can be turn on the T2. Suppose here is the T2 here. After some time, what will happen? So T2 will be turn on. After some time, T3 will be turn on. So after sometime T4 will be turn on. So like this current here, this anode current, the spread over the complete terminal or complete junction here. So now it takes some time. Okay, rate of rise of current is so like this. So that's why. So here is if it is this is suppose if rate of rise of current is a more greater than the specified value, so then what will happen? The local arc spots occur in the layer which is very nearer to the gate terminal, so which may damage the SCR. So how do we protect this from the local arc spots problem? So it can be protected by connecting one inductor in series with the SCR as shown in the figure. So why? Because this inductor, the higher inductor opposes the sudden changes of the current. Okay, that's why. So it takes some time to rise, or it takes some time to spread the current entire area of the SCR. Okay, so like this we can explain, like this is how local spots occur in the SCR here. So actually I have taken di by dt is I is equal to 100 amps, but I have divided into the 4 SCRs. So each carry the current of the 20 I. So this is the example point. What is the di by dt here? 30 amps per microsecond. So now here once gate triggered, this current passes the 25 amps, but the rate of rise of current is more than the current passes from the anode to the cathode terminal. So that's why your temperature rise will be increases. So now it can trigger the T2 and it takes some time, and it can trigger the T3, it takes some time, and it can trigger the T4, it takes some more time. So now after complete time, so now your total current passes to the here. So now your current is at 100 amps. Now which is less than the rated values. So that's why if the rate of rise of the current is low as compared to the specified rate of rise of the current, so we can protect the SCR. But if it is in order to protect the SCR, so there is one inductor is connected in series with the SCR. So this inductor allows opposes the sudden changes of the current. Okay. Okay, is that clear now? How di by dt protection takes place? So di by dt protection is next one, dv by dt protection. So this is the dv by dt protection. It is not di by dt. So this is the dv by dt is the rate of change of the voltage across the SCR here. So now to protect it from the triggering due to the I dv by dt, so snubber circuit is used. What is the meaning of snubber circuit here? So now this is the capacitor is connected. Okay, capacitor is connected snubber circuit is the simply that is the combination of resistance and capacitance which are connected across SCR as shown in the figure. Here. So now here resistance here capacitor can block the high rate of rise of the voltage, but resistance is limits the discharge current of the capacitor. Suppose here, so there is no this is the resistance, then what will happen? The discharge current of the capacitor is increases enormously, which can damage the SCR. That's why here resistance is connected in series with the SCR to limit the discharge current. Okay, so how do we design? Okay, this is the design of the snubber circuit element. So that is a very important part in this discussion. So how do we design the snubber circuit? Okay, all of you clear? So when switch is on, so then what will happen? See, when switch is on, okay, switch is on. So now current passes through the R, the S and also L terminals. Okay, like this. This is the RL here. Current passes through this L. Simply it is a RLC circuit. Okay. So once the SCR is triggered, this capacitor is a discharge. Capacitor current to the capacitive terminal. So now this is the initially when switch is on, current passes through. Okay, here current passes through RS, okay, CS, inductor and RL and comes back, okay, comes back to the source. Okay, this is the current directions here. So simply this circuit seems to be like one is the resistance R, okay, RS, okay, next one the inductor is a, okay, this is the L and it is a RL, okay, it is a initially capacitor here under this condition short circuited, so it is a charging condition. So next one, this resistance is a RL value here, okay, RL, the load resistance and the source resistance. So how do we find out this current, I amount of the current? So now it is a VS and it is a I amount of the current. So just apply the VA. So now R is equal to RS into, okay, RS plus RL into I, okay, RL into I plus L, so di by dt, okay, is equal to the VS value here. So now by simplification here, this value is equal to, so how do we get this one? Okay, here I of t is equal to, so just by using the Laplace transforms, so by Laplace transform, so we get I of t is equal to, so I amount of the current, or this is the IVS by RS plus, okay, RL 1 power e power minus t by the tau here. So where tau is equal to, so what is the meaning of tau here? So tau is equal to here. So this is the here VS RS by RL, that is the inductive term is there. So that is the tau is equal to RS plus RL divided by, sorry, this is the reverse, L by R. So tau is equal to L by the RS plus, okay, RL value here. So this is the current passes through here. So now let us find out rate of rise of the current, okay, di by dt. So how do we get di by, okay, di by, so dt value here. So how do we get di by dt? This is equal to the Vs by Rs plus RL, the multiplied by Rs plus, okay, RL, okay, divided by VL, so e power minus t by the tau. Okay, tau is equal to, you can write actually e power minus t by tau. Tau we can write directly Rs by RL by L here. So now this is the inversely proportional. So that's why, so this will be the cancelled out. Okay, di by dt is equal to, so now we can write here Vs by L, so e power minus t by tau values here. So from here we can write inductance L is equal to, So Vs di by di by the dt, or this is the Vs. Okay sir, just wait. Okay. Okay, di by dt is equal to Vs by Vl v power minus t by L. So now value of di by dt is a maximum. Okay, when it is maximum here, so whenever t is equal to 0, di by dt is a maximum. Di by dt is a maximum. Okay, maximum. So when the t is equal to 0. Okay, so that's why we can write di by dt maximum is equal to, okay, maximum is equal to the Vs by L here. So now from which you can write L is equal to Vs by di by the dt maximum value here. So this is the designing parameters of the inductance, the L value here. So where L is equal to the supply voltage divided by di by dt maximum. Okay. Now how do we find out the resistance, the how much amount the resistance one? So resistance you can write voltage across the resistance, the voltage the across the resistor. So that is equal to I into Rs. Okay, where I is equal to, so now this is the voltage across the resistor. So this value, so where I we can know that the I is equal to the Vs by RL, okay, RL plus R, okay, Rs. So 1 minus, okay, e power minus t by the tau value. This is the value. So now simplify this equation. So dVA by, okay, dVA by d maximum. So now this the dVA by dt is equal to R. So this value is a RA. So this by simplification you will get RA by DRS by the di by dt values here. So now simplify, okay, Rs divided by dt value. So dVA t by, okay, dt maximum, okay, this maximum is equal to, so now Rs, okay, it is equal to, so di by dt maximum value here, okay, di by dt max. So now we required Rs value. So how do we get Rs value? So now here is a this equation dVA by the dt maximum is equal to, so that value is equal to, so already we know that di by dt maximum, so di by dt maximum is equal to Vs by L. So now it is equal to Rs, okay, di by dt is equal to Vs by L. So now this is the value of, okay, so now from here the Rs is equal to, okay, what is the value of Rs? So Rs is a, so dV by a dt maximum, so divided by, okay, the Rs value, dV by here, so Vs by L value here. So this is the value of the Rs. So like this we have to simplify the resistance and inductance of the in snubber circuit. Okay, all of you got it? Any more doubt? Any more doubt from here? Okay. So now how do we protect the SCR from the gate? So now gate is a, we have gate terminal also, there is a, the one is a over current protection, and here, so from the over current protection a resistor is inserted in series with the gate terminal. So from the over voltage protection a GNR diode is connected, okay, across these two terminals, across the cathode and gate terminals here. And next one, a RC circuit is connected to protect the gate from the noise, okay, unwanted noise signals here. So now this is protect the gate, it is protected, it protect gate from, okay, from the over current here. So next this GNR diode protect gate from over voltages here. Now this RC circuit here, this is a protect gate from unwanted noise signal. Okay, these are the questions. Okay, 1 mark question point of view. How to protect the gate from the overcurrent? By connecting the resistor in series with the gate terminal. How to protect the gate terminal from the over voltage? It can be protected by using the ZNR diode. So next one, how to protect the gate from the unwanted noise signal or pulse triggering? So it can be protected by using RC circuit. Okay, these RC elements are connected across cathode and the gate and cathode terminal as shown in the figure. So now this is the protection of the gate. Okay, so over voltage, over current. The next one, the di by dt protection, dv by dt protection. dv by dt protection can be obtained by using the snubber circuit. So how do we design the snubber circuit element here? So when it is operated under snubber circuit condition, so the L is equal to, okay, L value is equal to Vs by dy by dt maximum, and also this is the R is equal to, so L by Vs, okay, dv by maximum 1 or dv by dt maximum Vs by L1. So this is the resistance. What is the function of the resistance here? So it is a conducted in this series with the capacitor to limit the discharging current. Okay. Next one. So another protection of the SCR, that is the thermal protection. So what is the meaning of thermal protection? So with increasing the temperature rise of the junctions due to any abnormal conditions, insulation may get failure. So SCR may get damaged. So heat sinks are provided. Okay, these are heat sinks are provided. Suppose we have the SCR like. So before the connection of the air, SCR is this is the SCR. So now here heat sinks are provided. Okay, these are heat sinks are provided. So this is called as the heat sinks. So in the bath, suppose, okay, this is the PN terminal. Okay, these are P and N terminals. P and P terminals here. Cathode and this complete inside the box is so now this is the SCR. Okay. Now here is heat sinks are provided. Okay, heat sinks attachment to the SCR. So to limit the temperature rise or to protect the SCR, so observe the internal power dissipation and maintain the temperature within the limits. So now here we have so there is how to design. This is the junction temperature junctions. So here SCR. Okay, this is the case. Okay, and next one heat sinks and atmospheric or ambient temperatures here. So now this is the first one, temperature changes from the junction to the cases. Okay, junction to the case. And after that, the temperature changes from the case to the heat sinks. Okay, heat sinks here. So now this is the heat sink. And after that, the temperature changes from the heat sinks to the atmospheric conditions. Okay, outside. So now initially this is the more temperature changes from that. This is the thermal potential difference, like thermal temperature difference. So now here this is the temperature difference from the case to the sink. So here J in the sense junction. Okay, this is one is the junction, and where C in the means, okay, C is nothing but here case, and this one is the S is the sink. Okay, and A is the atmospheric temperatures here. So now here temperature changes from the junction to the case and case to the heat sink and heat sinks to the atmospheric. Okay, so like this here temperature changes from. So how do we model? Okay, this is the modeling here. So always, okay, in the electrical circuit point of view, suppose this is the the circuit elements. Okay, electrical circuit elements. Okay, elements here, or otherwise, okay, electrical circuit elements. Okay, next one, the thermal, the elements. Okay, what about the thermal, the equivalent circuit elements here? So now here is in the electrical circuit, charge flows from the one potential to the another potential. So now this is called the charge flows from the one potential to the another. So now in the thermal circuits, then is a heat transfer from the one junction to the another junction. So now it is a heat. So next one, potential difference. Okay, potential difference. So that's we call in the electrical side voltage difference between the two potential, EMF or potential difference here, voltage. So now in the mechanical circuit, the mechanical analogy, so how do we represent this potential difference here? The temperature difference. Okay, this is a temperature difference here. And next one, the current flows from one point to the another point. Potential difference and charges flows is here. So current here, this is the current flows from here to here. So next here is a thermal power loss. Okay, thermal power loss is here. So thermal average the power loss in the mechanical side. And next one, the potential current, and also what about this resistance element? Resistance opposes the flow of the current. Similarly, thermal resistance opposes the flow of the heat, flow of the, so this is the power losses here. That is equal to the thermal T, okay, is the thermal, the resistivity, okay, not this one is the resistivity of the electrical circuit. So by using this, you can draw the equivalent circuit of the heat sinks. Okay, how do we draw the equivalent circuit? So let us assume this is the Tj, okay, temperature at the junctions, temperature at the cases, and temperature at the heat sinks, and temperature at the atmospheric. So now what will happen here? Average power loss is equal to P average. So now here, just like a current flows in this all the element. So now P average is equal to, so now we can write temperature changes from the junction to the temperature changes from the junction to the case. So divided by T, okay, thermal resistivity from the junction to the case. So this is equal to the temperature changes from the case to the heat sink, okay, case to the sink, okay, this is the T, the theta Cs, okay, thermal resistivity between the case and the sink. Similarly, this the temperature changes from the sink to the atmospheric. So now this is the divided by theta SCA1. Suppose we require total power loss, okay, complete power. So power losses from the junction to the atmospheric. So how do we get the average power losses is equal to, so now here Tj minus Ta. So Tj minus Ta is equal to, okay, this is a Tj minus the Ta is equal divided by, so now total thermal resistivity Tjc plus, okay, Tcs, okay, Tcs, the plus theta Sca here. So now this is the total average power losses. Okay, this one, in order to limit this to value, the heat sinks are provided here. So now how do we get rating? Okay, we know power rating is equal to, okay, always we know that. So power is equal to I square R ratings. Okay, so now here the rating is a directly proportional to rating of SCR, the directly proportional to the here the average the under root of average power losses here. So therefore we can write the rating of SCR. So that is a directly proportional to, we can write under root of P average, okay, P average square. So now this P average square in the sense, so under root of Tj minus Tt. So now it is a Tj minus, okay, Tj minus, okay, Ta. So divided by the theta Ja, where theta Ja is equal to, so what is the theta Ja here? Total the thermal resistivity. So theta Jc plus, okay, theta Cs plus theta Sa. So this is the one of the equation. How do we find out the rating of the SCR by using the temperature here? So always rating of the SCR is inversely proportional to the average power loss. Under root of inversely proportional to average power losses here. So this is the complete the circuit of Okay, suppose if we draw the complete circuit, protection circuit, how do we draw here? Okay, suppose I have drawn individually. Suppose this is a one SCR. Okay, SCR here. So each sinks are provided the SCR. Okay, each sink. And this one is the gate terminals. Okay, gate terminal here. So now inductor is connected in series with the SCR. So to limit the di by dt. Okay, this is the inductor is connected. So to limit the di by dt here. And the circuit breaker and the fuse is provided. Okay, it is a combination of so circuit breaker and the fuse. Okay, circuit breaker. The plus fuse is provided. Okay. So this is the positive terminal and this one is the anode terminal and this is the cathode. So connected to the positive supply and negative supply. Okay, it is the VS1. So next one, the gate is the protected and it can be protected from the over voltages. So now it is protected from the over current. Okay, over current. So now it can be protected from di by dt. Okay, this elder. So now here this is a varistor is connected across the this SCR. So this is the completes the protective circuit. So this is the varistor, non-linear metallic the resistor that's we call varistor. It is connected across the SCR. So it is the anode and it is the cathode terminal. So next one, the snubber circuit is used also connected. So snubber circuit is the resistance and also the one combination of the resistance and so this is the capacitance. Okay, capacitor is connected like this. So now here to the this diode is also connected across the resistor. So now this is another one. So diode also connected in the snubber circuit here. So this is a complete snubber circuit. This is a complete protection circuit here. So now this can be protected from the over voltages here, and it is protected from the dV by the dt protection, and this is a di by dt protection, and the gate terminals here. Okay, here in order to the protect the gate here, the resistance is connected and another the parallel resistance and capacitor is connected from the over voltage to protect the over voltage. And next the noise protection, one Zener diode is provided here. So now it is a over voltage, the over resistance R2 and here R1 and the C. So it is a protect the SCR from the unwanted gate signal, and it is a this is can be protected from. So these are with respect to the cathode. So over current and overall. So this is a complete circuit is known as the protecting circuit of the SCR. Okay, this is the designing parameters and also protecting circuit of the SCR. Okay, all of it clear now? Okay, is that clear? Okay, now we can ask any doubt. So let us end the session. If you have any doubt, you can ask. Otherwise, I will stop the class here. Okay, this is the benefits of Iconic and Place subscription. So by taking the Place subscription, you will get the live classes, okay, structural schedule, unlimited practice question, and test series. Okay, by taking Iconic subscription, you will get personal coach, study planners, expert guidance, and ESC mains and questions. Iconic subscription is the best suitable for ESC preparation. So it is a official Creatrix channel which has 150k plus members. So please join in this channel for any updates from the Creatrix team. And it is Unacademy GATE Telugu channel. So for any updates from the GATE Telugu team, so please join in these channels. Okay. And it is these are the different type of channels under the Unacademy. One is the Creatrix GATE, Unacademy GATE Civil, Unacademy GATE Mechanical, okay, Computer Science, GATE Questions, Electrical Junction, Engineering Foundation in Engineering Pathshala. So this is our channel. So please like and share, subscribe this channel. Okay. Thank you all. Thank you very much. Tomorrow we will discuss the problems based on this concept. All the question series. The problem based on the thermal protection, okay, snubber circuit, okay, snubber circuit problems are very important for gate point of view. So thermal protection problems are also very important, and also based on the ratings, surge current rating questions are there. So I will discuss all the problems based on this concept. Okay, so tomorrow class is very important. Thank you all, thank you very much.